In the last video, we introduced the electric field, and now I'd like to get a little more quantitative about it and also take a look at applying superposition to electric fields. Since the electric force obeys superposition, which means that we can treat interactions between charges a pair at a time, it'll follow that the electric field also has to obey superposition. So if I want to find the electric field at a particular point, I can look at each individual source charge one at a time, find the electric field due to that source charge, add all of that up, and then that will give me the electric field at that particular point in space. So the example I'm going to start with is what's a construction known as the dipole. Dipoles show up a lot in atomic and molecular situations because of the fact that in an atom, unless it's ionized, it has the same number of protons as neutrons, and so there'll be an equal number of positive and negative charges. And sometimes it'll be the case that considerations of how the molecule is bonded or whatever will cause there to be a slight separation between where the middle of the electron cloud is and where the nucleus is. But let's just go ahead and take a look here. So I'm going to go ahead and take a look at this one here. Let's say this is physically, you could maybe build this in a student lab charging little bits of styrofoam or something like this. We'll say that this is a charge plus Q, this is a charge minus Q. So it's the same magnitude charge, and to make it concrete here, let's say that the magnitude of each of these charges is 1 nanocoulomb. Now the separation of our dipole, which is usually denoted with the letter S, let's make it 1 centimeter. Now, if this were an atom or a molecule, we'd be talking something like 10 to the negative 10 meters. But here, if we're imagining like a couple bits of charged styrofoam, something like that, where a centimeter separation seems reasonable to me. Now, let's say along here on the y-axis, let's say this is my point of interest right here. And now I'm also going to say this is not to scale. Let's say that the distance from the center of the dipole to my point of interest is a meter. Again, perfectly reasonable if we're playing with little bits of styrofoam. What I would like to know is what is the electric field due to the dipole at this location. Now, there are going to be two contributions to the electric field. One is going to be from the positive charge, and there the electric field at this point, due to this charge, is going to point up. So we'll call this contribution from the positive charge, we'll call that E+. Similarly, the negative charge is going to have a contribution pointing down. And I intentionally drew it shorter, E-. Intentionally drew it shorter, and this is because this point is slightly further away from here than here. It looks a lot further away because of how I drew it, but again, remember that this drawing is not to scale. This point here is about 100 dipole separations away from here. Okay, so anyway, we can go ahead and add the vectors up. In this case here, I think I will go ahead and revert to the good old tail to head rule. So I'm just going to put another copy of E- right there, like that. I just did a parallel transport so I could put the tail to the head. And then I get that my net electric field from the dipole points up. So we'll say E dipole points up. Now, what I want to point out here is we'll see that these two contributions are actually very similar. They should be drawn to be almost exactly the same length. I intentionally distorted this a bit because if I didn't, I would actually have a very hard time drawing E dipole on the screen. But let's go ahead and calculate this out. So the electric field for the dipole in magnitude, this is going to be the magnitude of E plus minus the magnitude of E minus, because E minus is pointing down. All right, so this is our point charge here. So this distance, so the first distance we care about for figuring out a strength is going to be this distance right here. So the distance from the origin up to my point Y up here, we're going to have this distance here is half of S. So that makes this distance Y minus S over 2. And while we're at it, I'm going to go ahead and dimension in for the negative charge. That will be a distance of Y plus S over 2, because relative to the center of the dipole, this is half the dipole width further. All right. So putting in, this will be K, absolute value of Q, over, this will be this distance right here, Y minus S over 2, and that's going to be squared, minus KQ. Now be over the square of this distance, Y plus S over 2 squared. So remember, the contribution to the electric field strength from any charge is going to be KQ over the square of the distance from that charge to the point of interest. And again, this minus sign is because they're working at cross purposes, so they're canceling each other out, although we can see it won't be a complete cancellation. All right, just to clean up the algebra a little bit, I can pull a K and a Q out of everybody. I'll have 1 minus Y minus S over 2 squared minus 1 over Y plus S over 2 squared. And if you want to, you can go around and clean this up. I think we can just go ahead and stick the numbers in now. So this is going to be, our K is 9 times 10 to the 9 Newton meters squared per Coulomb squared. I said our charge was 1 nanocoulomb. The nano prefix means 10 to the negative 9. So it's 1 times 10 to the negative 9 coulombs. Gonna need a little more room here, so I'll do that. And then we're going to say times 1 over, this is 1 meter minus a centimeter is 0.01 meters divided by 2 squared minus 1 over, same thing but with a plus. Okay, grind all that through your calculator. You get that the electric field strength is 0.180 newtons per coulomb. Now, that is a decent amount. Certainly something you could measure, especially if the piece, if you're using little bits of styrofoam or something like that. But for point of comparison, roughly, both E plus and E minus are roughly 9 newtons per coulomb. So basically all but 2% of the force that each of these is exerting, roughly, got canceled out. 98% of it got canceled out, and we only got this little bit left. And that's pretty impressive. As you get further away, this difference drops off even more quickly. Okay, so let's go take a look at another scenario for the same dipole pair. So that's what we call an on-axis configuration when you're interested in a point that's on the dipole axis. Another one that people often think about is what's called off-axis, which is where you think about a point. So plus Q minus Q. We'll again say that Q is 1 nanocoulomb. 1 nanocoulomb. We'll again say that the separation between my charges S is a centimeter, like so. And this gets called the off-axis situation here, where we're interested in, or our point of interest, and still this is not to scale. Our point of interest is perpendicular to the axis of the dipole. And again, I'm basing it off from the center of the dipole, like so. So let's again make it 1 meter. This time we'll call it X. And again, I want to find the total electric field contribution from the dipole. Now, in this case here, you would be expecting that it's not going to be terribly big, and you would be right. At 1 meter away, that's 100 times this separation here. If you were about 100 times the separation of 2 car headlights away from a car, you would be very hard pressed to tell if you were looking at 1 or 2 lights. So at the scale I've got this drawn, these 2 charges are almost on top of each other. So you'd expect things to almost cancel. Again, I'm drawing it off scale a bit, not to scale here again, just because I want to make it a little clearer what I'm drawing. So I'm just drawing a little work line here. The electric field at this point, here, due to this charge, has to point directly away from the charge, like so. That's my E plus. And similarly, my E minus, it's the same distance away this time. You should be able to convince yourself of that. And it'll be headed directly towards the negative charge if I can do decent art. I tried really hard. There we go. E minus, something like that. And there we go. It's on the line that brings us to the negative charge. Okay, so once again, I'm going to go ahead and add these up using the tail to head rule. So I'm going to make another copy of my E plus right here. I'm just doing a parallel transport from what I had before. So there's my E plus, and I get that my net contribution, adding up E plus and E minus as vectors, points straight down. All right. So let's go ahead and just write expressions for what the magnitude of E plus and E minus are. So E plus will equal E minus. That's going to be equal to K times Q over whatever that distance is squared. Well, let's figure out that distance. This distance here is, well, if I go up this much, go over this much, that's X. And if I go up this much, that's S over 2. And since this is the hypotenuse of this right triangle, by the Pythagorean theorem, this distance will be the square root of x squared plus s over 2 squared. But I need to square this distance when I say kq over r squared. So that's just going to be x squared plus s over 2 squared. And that's the strength of both of them. The only reason they aren't going to add to 0 is because they aren't pointing in the same direction. So let's go ahead and take care of that. You should, I hope, be able to convince yourself that this angle here between these 2 work lines and this angle here between these 2 vectors are the same by alternate interior angles. And since they're otherwise both isosceles triangles, that means that this vector triangle that I drew here is a similar triangle to this physical triangle right here. So let me just go ahead and highlight those. So here's the physical triangle I'm thinking of right there. And here is the vector triangle that I'm thinking of right there. Those are similar triangles. So what this means is I can set up a proportion. I can say that E dipole is to E plus. I could choose E minus. It totally doesn't matter because they're both the same. That has to be the same. The equivalent of this over here on the physical triangle is S. And then the equivalent to this is this hypotenuse bit here, x squared plus S over 2 squared. All right. So this gives me that my dipole strength, dipole field, is going to be E plus times S over the root. So this will be KQ over x squared plus S over 2 squared times another S over square root of x squared plus S over 2 squared. All right. So since this is the square root, and the square root is the same thing as raising something to the 1/2 power, you can rearrange this to be KQ times S over x squared plus S over 2 squared raised to the 3/2 power. All right. Now let's go ahead and plug in the numbers here. So this is going to give me 9 times 10 to the 9 Newton meters squared per coulomb squared. 1 nanocoulomb is 1 times 10 to the negative 9 coulombs. 1 centimeter is 0.01 meters. This will be over 1 meter squared plus 0.01 meters over 2 squared to the 3/2 power. Grind that out, you get 0.0900 newtons, or basically 1% of the strength of either of the charges individually. So 99% of their influence cancels out, and you're left with just 1% of it. And again, in either case, I've now calculated what the electric field is at that point. And if I choose to put electric charge at that point, sorry, newtons per coulomb, if I choose to put a charge at that point, to find the electric force on that charge, I would take that 0.09 newtons per coulomb, times it by however many coulombs of charge I put at that location, and that's the force that it will feel. Okay. Now, I can't derive this without the use of the methods of calculus, other than to say it's in the very same spirit where we just go ahead and continue adding up whole lots of charges just using the methods of calculus. But there is a particular electronic device known as a capacitor. And what a capacitor is it is 2 plates. If it's an electronic device, it usually the plates, well, it doesn't matter what the shape is. We'll get into that later. But you have 2 plates. I'm kind of looking at edge on. They're separated by some usually fairly small distance d. And one of the plates will hold a charge of plus q. The other one will hold a charge of minus q. And if usually we assume that the separation d is small compared to plate dimensions. That means in that case, almost everywhere inside the capacitor. You can pick basically any random point anywhere, and you'll have an electric field vector that points away from the positive charge towards the negative charge, and the strength of it will basically be the same. And this comes from just using the methods of calculus to add up all the contributions to all the electric fields from the positive charges and from the negative charges, just like we were doing with that off-axis dipole thing. There are some issues when you're right at the edges, but again, I will defer treatment of that till later. Anyway, the electric field strength for this will be the magnitude of the charge on either plate, big Q, over epsilon naught A, where A is the area of either plate. And the direction will be from positive to the negative plate. And outside the capacitor, the strength of the electric field is very nearly zero. This number, epsilon naught, it gets a really fancy name. It's called the permittivity of free space. It is 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. Now you might look at this and say, hey, isn't that the inverse of the answer K? And it is. K, our electric constant from Coulomb's law, is often can also be written as 1 over 4 pi epsilon naught. And depending on computational convenience, you can either write K or you can write 1 over 4 pi epsilon naught. It basically depends whether they need to cancel some 2's or pi's or not. All right. So let's just take a look at one more problem. So let's say you had an electric field that got made uniform by a capacitor or something like that. So let's say we are in a region of uniform electric field. So let's say it's pointing to the right. And then what I will do is I will release an electron. So initially at rest. Let's let it travel let's let it travel a millimeter. So the electron will feel an electric force. So what we want to know is which way did the electron go, and how fast is it going after it travels 1 millimeter. All right, well, first off, let's just start with the which way part. So what I want you to do is right now go ahead and think about which way did it go, and then so pause the video and get back with me. All right, so hopefully we are in agreement that the electron is feeling a force, an electric force to the left. And remember, this is because F equals QE, where Q is the charge I put at the location. And here, the charge is negative E. Just a quick reminder, in physics, all constants are positive numbers. So the official name of E is actually the fundamental quantum of electric charge. And the charge on the electron is minus E. So anyway, so the point here is that the electric force is going to be some negative number times the electric field, which means the electric force points anti-parallel to the field. So since I had the field pointing to the right, the electric force is to the left. Since we're initially at rest, that forces us to move to the left. All right, so then the rest of this is doing kinematics. So we may as well go ahead and say, we'll go ahead and let x positive be to the left here. So we'll say we travel delta x equals 1 millimeter like this. This is my x initial, that's my x final. V initial is 0 meters per second. What is my V final? And so if we think right off about what we know and what we don't know, we know the change in the position. We are being asked for the final velocity. We currently do not have either the time of flight or the acceleration. So in order to be able to solve the kinematics problem, we need to find one of those. In this case, we can find the acceleration by Newton's third law. We can say that A equals F net over m. In that case, that will be the electric force over m, which will be QE over m. Now this is different than it was with gravity. Remember, with gravity, this would have been an mg up here and an m down there, and the m's would cancel. Not happening with the electric field. That's how the electric force is different than gravity. All right, but now we have A, and so we can use the kinematics equation that does not have time in it. So that's V final squared equals V initial squared plus 2A delta x. V initial is 0. A is QE over m. And I have a delta x there. So my V final will be the square root of that. And we should be working, since I'm working in magnitudes, we'll take the absolute value of the charge there. So this will be 2 times the absolute value of negative E delta x over m. Absolute value of negative E is just E, 2E delta x over m. And now we're ready to put in the numbers. We get that this will be square root of 2 times the charge on an electron is 1.6 times 10 to the negative 19 coulombs. Again, the magnitude of the charge, we've already handled the plus and minus signs. Said our electric field strength is 500 newtons per coulomb. And we said that we are traveling 1 millimeter, which is 1 times 10 to the negative 3 meters. And the electron mass is actually kind of easy to remember. I always think call 911, 9.11 times 10 to the negative 31, the ones in the 31 rhyme, kilograms. All right, and that will give us 4.19 times 10 to the 5th meters per second. So about 0.13% of the speed of light after having just traveled a millimeter. That's pretty impressive. This is both a testament to the strength of the electric force and also to the extremely low mass of the electron. All right, so in the next video, we'll go ahead and take a look at electric field lines, which is in sort of an artistic way for us to figure out how to get electric field vectors and without having to do lots and lots of math. So, all right, we'll catch you in the next video.